All right, and recording is rolling. So today is Monday, November 29th. Welcome back from that very long, nice Thanksgiving break. Right, so you guys remember before the break, I gave you guys notes on rotational dynamics, which were these topics here. Looking at some rotational kinematic motion. We did revisit centrifugal force from Unit 3 by AP's book. We looked at rotational inertia, torque, and then some other rotational concepts, kinetic energy in a rotational context, and also momentum in rotational context. Okay? So you guys have the notes on these notes from a while back, but we're going to get into the book columns today. Now, the textbook columns, page looks like this. I gave this to you guys a long time back also. Remember, all these are, if you lost this, all these pages are on Google Classroom, because everything is to Google Classroom. Okay. There's also Unit 7 multiple choice questions on AP Classroom. Let's have those due 1 week from now, the AP Classroom questions, one week from now, so that next Monday or Tuesday I can go over those in class. Okay. These textbook problems that I'll get probably about halfway through today, let's have those due not this coming Friday, but the next Friday, which would probably be plenty of time. There's also a bunch of labs that I'd like to fit in, and even FRQ and Kahoot if we have time, but we'll see. Midterms are coming up. So I do have a midterm review for you guys. This is clipped to the front of your desk, this half page. Okay. So the midterm is going to be part multiple choice, and also I'm going to throw in a couple of free response questions, but I'll do a few days of review so you guys have plenty of heads up and review about that. Of course, I'm never trying to trick you guys, but just give you guys some good challenging questions, and I'll do that. All right, so you guys ready to get rolling on these rotational dynamics questions? Yeah, you have a question?
Is like that way we can check our answers to like these questions?
Yeah, I'm going to go over all those questions in class. Yeah.
Oh, okay.
Yeah.
Are we gonna go over them like right before the exam or like throughout the week?
Yeah, I'll take a few days. Right.
Okay.
So yeah, we have they just released the midterm schedule like an hour or two ago. So I have to I'll get that to you guys soon too. But yeah, we're gonna do all this rotational dynamic stuff. Got all these problems, got these labs. I'll get a quiz to you guys, and then that'll be the last one for the midterm. Then I'll take a few days to go over the midterm review. Okay. So chapter 8 questions. Okay. First few are from this warm-up section. Thought there were some good questions here. Let's look at number 3 from the warm-up. A spinning wheel steadily slows from initial angular velocity of so many revolutions per second to a smaller number of revolutions per second because it's slowing down. And it does that all in this time interval. Calculate the wheel's angular acceleration in radians per second squared. And then there's a follow-up question: what angle does it go through? Say, how far does it spin? Give you guys a model real fast. Zoom out here. You guys remember this turntable spin? Okay. Like right now, this wheel is spinning at pretty much a constant angular velocity, right? There's a certain rate of spinning. Like for example, the Earth spins once every 24 hours. That's pretty much a constant value. Okay. So really similar idea here. Okay. But if I just let it go, it's going to slow to it's going to slow down. Right? What rate is it slowing down? That's the first question. Now the follow-up question, part B, is going to be, well, how far did it turn? Right? How many revolutions did it turn? Okay. So number 3, turntable. Okay. Now I'm going to make up my own numbers like I usually do. Let's say omega naught is, they said 2 revolutions per second. Maybe I'll make mine 3 revolutions per second. 3 revolutions per second. And then they said it slowed down. Maybe I'll make this other one like 1.5 revolutions per second, something like that. And did that all in a time interval of so many seconds. Maybe I'll call this 8 seconds to do all that. Okay. Hey, does that look like 3 kinematic values? Maybe you should sort of think like a taxonomy table. So there's 5 variables that we could be juggling. We have 3. That means the other 2 are solvable. And actually, the other 2 are the 2 questions. But you know what? They actually gave us these angular velocity values in units that are not directly applicable. Why? What should I do with these numbers first? Convert them. Yes. I don't want revolutions per second. I want what? Radians per second. You guys remember that there's three main ways that people measure how far something's turned? Right, well, not only three, but three main ones, right? There's degrees, like maybe I could say this made like a 30-degree angle turn. Right? There's also revolutions, like one full spin is one full revolution. I mean, that's pretty intuitive. Right? But then there's kind of an abstract way that you probably learned just in high school, which is how many radians, right? How many radians. But that's actually the most useful measurement because that's the only value that you can directly plug into equations. Right? Like anytime we've done a calculation with degrees, if you paid real close attention, it's always been in like a sine, cosine, or a tangent. It's never been directly multiplied by something. But if you want to apply those kinematic formulas, like you guys see them up here on this poster, right, looking at these kinematic formulas right here, okay, you have to be using radian values. So let's convert. I'm going to use sort of a dimensional analysis table process. Okay. So I don't want revolutions, I want radians. Do you guys remember how many radians are equivalent to one revolution?
2 pi.
2 pi, exactly. One revolution is exactly 2 pi radians. Do that for both of these, 2 pi radians and one revolution. Okay. If you ever forget that, there's, I bet you guys know a formula that says circumference equals 2 pi r. Right? If you ever want to know like the distance that a point is moved as it's spinning around, like this point right here, right? You say, well, if I know this radial value r, I multiply by however far it's turned in radians, then that'll tell me how far it's moved. And if that happens to be 2 pi radians, well, hey, that would be one trip around the circle. That's why circumference equals 2 pi r. Right? Yeah, so 2 pi radians is one revolution. Right, so let's see how many revolution cancels. Let's see how many radians per second each of these is. So I'm looking at this many radians per second. Oh, whoa, something just messed up. What? 3 times 2 pi? Oh, sorry, that's 18. So here, 18.85. There's that. Okay, there we go. All right, so let's spin in this fast, now it's spinning this fast, and it does that all in this amount of time. Right? All right, so look at those formulas, say on that poster over there. Which one's probably most directly going to lead you to solve for alpha, the rate that it's slowing down? First, second, or third? Second one. Yeah, definitely second one. Okay. Omega final equals omega initial plus alpha times t. Okay. The final speed is equal to initial speed plus acceleration times time, sort of thing. Right? And we're solving for this. You know what I'm going to do is actually rearrange this in terms of variables, because maybe it's possibly more intuitive to your brain to think about it in this way from the start, right? I mean, acceleration is rate change of velocity, right? You take this, just rearrange it, just turns back into that, right? Right, so that's going to be omega final is this number, radians per second. Omega initial is this number, radians per second. So there's the change in velocity, and here's the time interval that all happens in. It's going to give me some radians per second squared. So it is looking at, well, it's going to be a negative value, right? Everybody's going to be negative because it's slowing down. Radians per second squared. Okay. So according to my numbers, my turntable is slowing down by 1.18 radians per second every passing second. That's the rate it's slowing down. Now, notice this particular scenario, it hasn't really come to a full stop at this point. It's just slowing down at that rate for that time. Okay. that was part A. Now part B says how far did it turn, which is going to be some number of radians, right? If you just apply the equations. Now here I've got an option. I could pick either that first or that third equation. Okay. I'm going to pick the first one because it's already algebraically set up to solve it. You guys remember x equals v naught t plus 1/2 at squared? Well, it's just analogous to that. Theta, how far it turns in radians, is equal to omega naught, initial angular velocity, times t, plus 1/2 alpha t squared, where alpha is what we just found, the rate slowing down in this case. Okay. Now this has to be a negative number, so it's all good. Okay. So I got the initial angular velocity was this many radians per second. I have to be using radians per second. Radians per second. Okay. Did that for this many seconds. Plus 1/2 alpha. Now alpha is negative. Slowing down. Radians per second squared for this amount of time squared. All right, there we go. All right, I'm looking at this many radians. That's how far this thing turned. Get to it? Okay, so that's all the book asks, but I have my own extended questions. Who can tell me how many complete revolutions is this equivalent to? How many revolutions is that? How many full turns did that just make?
Wait. You just divide by 2 pi?
Yep, that's it.
So like 18?
Yeah. That's what I'm getting. Right. So let's see. Take 113 radians. I know that there are 2 pi radians in every 1 revolution. Right, radians, and then get some revolutions out. Can I say this? 113 divided by 2 pi. Is that going to give me the answer?
Put in parentheses.
Parentheses, right? Just a little trick. I'm sure most of you guys got this by this point in the year, but if I type it like that, what the calculator does is it divides by 2 and it stops dividing and turns around and multiplies by pi. It gives me something that's totally wrong, right? But Ryan told me what the right answer was. It should be, there we go, about 18, right? So that'd be, yeah, let's call it 18 revolutions. Okay, like that. And the other follow-up question I have is, I wonder if you guys remember how to turn this into a graph, and specifically thinking of omega versus time graph. So let's do omega in radians per second and time in seconds. So for the whole scenario that we just did, for basically this story that was given to you, can you guys draw that graph? It's going to give you guys a head start. Okay. I see some of you guys are close. All right. What do you guys got here? I didn't see everybody's paper. I know. I'm sure some of you guys got it. But here we're looking at having an 8-second interval. So we're looking from time 0 to 8, right? So 8-second interval. Okay. Remember, initially it was spinning really fast, and then after a while it slowed down, right? So 18 to 9, sort of. Let's look about 18.85 to 9.42. Okay. So it was initially spinning this fast, but then after 8 seconds, it's only spinning this fast. Okay. Now, if you assume a uniform angular acceleration, then that's your graph right there. Okay, it's like slowing down, spinning.
Is this kind of like a velocity graph?
Yeah, because this is a velocity versus time graph, just angular velocity, right? Yeah, that is like that. What property is the slope? It is angular acceleration. And remember how it was a small negative number? Because that's a shallow negative slope. That's that, isn't it? What about the area of this trapezoid? What does the area of this trapezoid represent?
I know.
Yeah, how far? It was fun. About 113 radians. Okay, so this is negative 1.18 rad per second squared. I mean, run these numbers, that's what you're going to get. Okay, and you find the area of that trapezoid? I bet you dollars to donuts. It's going to be 113 radians. All right, number 10. What is the magnitude of the angular acceleration of, say, this mass disk, so so many kilograms disk, with a radius of so many meters, when a torque of magnitude of so many Newton meters is applied to it? Okay. Figure this out. Number 10. Yeah, this one. Okay. Actually, you know what I'm going to do is I'm going to change it just a little bit. No, here. They told you the mass of this thing is so many kilograms. Oh, I'm going to change it a little bit. Maybe like this many kilograms. They told you the radial size of it. So got a radius of trying to figure out these numbers here. Okay. I'm going to call it a radius of 0.80 meters. Okay. Now, sorry, they did give that to you too. Okay. What they did not give you, where I'm going to make a change a little bit, is the force applied at the edge. Okay. And I'm going to call it 50 newtons. 50 Newton force. Okay. And they want to know what is the rate that it's speeding up spinning. Say if it starts from rest and maybe you got a string wound around that and you start pulling a string with 50 newtons of force, it's going to speed up spinning. Okay. What is the angular acceleration? How do you figure that out? Right? Now, do you guys see that if you apply a force at some radial arm distance, and these are always going to be at a right angle to each other, you guys remember how torque is equal to R cross F? You guys remember that? Okay. And if you got a radius of 0.8 meters and a force of 50 newtons, I see that's going to be a torque of 40 Newton meters. I see that? Okay. Now, actually, your book did give you that. Okay. They did not give you the force, but they did give you the torque. But I'm just going back a step and saying that's what would have led to that point. Okay. Is that? Okay. But you know what? There's actually a different perspective on torque. Okay. This is one formula for torque. I think it's the way that I introduced it to you guys. It said every time you open the door, you apply a force on the doorknob that's opposite the hinges, so you get a nice wide radial arm. It gets a turning moment called a torque. Okay? But there's another formula for torque. You guys remember what the other formula for torque is? That is analogous to Newton's second law of motion? I times alpha. You guys remember this? Okay. This is analogous to F equals ma. Okay. So if something's rotating, remember now it's not just how massive is something to represent the inertia, but it's also how's that mass distributed. Okay. You guys remember, for example, like these meter sticks going on? Okay. Remember that I have a couple of meter sticks. Right? One has these masses pretty close to the center, so if I grab it by the center, shake it back and forth, real easy. Hardly any inertia at all. So if I take these masses and I push them way far out, the whole meter stick has the same mass, same weight. But if I try to shake it back and forth, it would be really hard to do if they were push way far out because mr squared, that would pump up this I value really big, wouldn't it? Right? So what's the alpha, like the angular acceleration, able to be? Based on some torque? Well, depends on what how the mass is distributed. Right? Hey, if I know what the torque is, because that was given, comes from R cross F, right? And if I were somehow able to figure out I, because it is related to M, but it's not just M by itself, but something, right? Then you could solve for alpha from there, couldn't you? You see that? Sort of like a game plan. All right, now here's where you have to make an assumption. You have to assume something about the mass distribution of that disk. Okay? Now, if you assume that it's uniformly distributed, wouldn't that make it like a solid cylinder? Like a solid cylinder shape? Hey, maybe kind of like this turntable. Like this turntable is basically pretty close to a solid cylinder, right? As it's turning. Right? And that's where you need this table from your book. Right now, you guys, college physics is on page 257. You guys remember this table of rotational inertia values? Okay. So for a single point, it's just mr squared. In fact, for a ring where every single point is equidistant from the center, that would obviously also be mr squared because every single point is mr squared. So just aggregate effect is also mr squared. Okay. But if you have, say, a solid cylinder, then remember how some of those points are distributed closer to the center, so they don't add as much rotational inertia compared to if they were all pushed out on the surface. So the aggregate effect is, say, half mr squared. It works out for a solid cylinder. And then for these other shapes, it's some fraction of mr squared. Remember, the bowling ball is 2/5 mr squared. The basketball is 2/3 mr squared. And then you have like lines that could swing around. Maybe sort of model a door, right? Like that. Okay. 1/12 ml squared and 1/3 ml squared. Something like that. Okay, so we're interested in this one. I'm going to assume it's a solid cylinder. So 1/2 mr squared. Guess that? 1/2 mr squared. Okay, let's use that. So we got torque is equal to I alpha. Okay. But that I, we're going to treat this as a solid cylinder and say it's 1/2 mr squared. Okay. As long as this is a solid cylinder, like a solid disk. All right. Maybe let's go ahead and plug in some values now. Okay, so know the torque, we figured that out already, but or the book gave it to you, one way or the other. So many Newton meters is equal to, okay, 1/2 mr squared. So it's your 1/2. The mass was given. Now I changed it from the book value just to make it a little different, but so many kilograms. Okay. The radial size was, say, this number. And don't forget to square that. Okay. And then all times alpha, which we're solving for. Okay. So if you put a torque on this disk, and it's this massive distributed this way, has this rotational inertia, then it's going to speed up spinning at some rate, and that's what we're trying to find. So shouldn't I just take all this bracketed stuff and just divide it down? You guys can do that algebraically, right? So take your 40 Newton meters, divide by this whole expression right here. Now just to be safe, open a bunch of parentheses. 1/2 mr squared. Okay. I'm getting alpha is equal to this many. This many what? What's the unit for that? Exactly. I hear a bunch of guys saying that. Radians per second squared. Yeah. Good call. Okay. That's the rate it's speeding up spinning. It's gaining 3.57 radians per second every passing second. Speeding up. Right here. Right, number 12. A bowling ball with mass so many kilograms. To go from kilograms to pounds, multiply by about 2.2. That's as much as I know. So this would be about 15 pound bowling ball. It is rolling at so many meters per second along a level surface. Okay. Right. Calculate. Right. There's a bunch of little parts here, but right. Calculate the ball's translational kinetic energy. So that's like traditional kinetic energy, just linear kinetic energy for 1/2 mv squared. Part B, the ball's rotational kinetic energy, because there's some energy involved with rotating about its own center, right? It's like the first one is if you point a radar gun at it, right? How fast is it moving linearly? So there's kinetic energy associated with that. But part B is saying like even if it wasn't moving forward, it's still spinning, and there's energy associated with that. Okay? Part C, the ball's total kinetic energy. Well, it's probably just the first two added together, right? Okay. And then part D, how much work would you have to do to bring the ball to rest? Let's say you're in front of the bowling ball, you're trying to stop it. How much energy do you have to apply to stop it? Well, I bet it's just equivalent to whatever kinetic energy, just the negative of that. Okay. All right, let's solve this one. Okay. Number 12. Okay. So we got this bowling ball. Actually, you might be thinking that it might not seem like they gave you enough information. Hopefully you had that thought, because I had that thought too. But let's give this guy a mass. I'm going to change the number like I usually do. Call it like 5 kilograms. Okay. Now this thing is moving. It's some v, some speed, which they did give you. So maybe I'll make it like this many meters per second. Okay. But it's also rotating at the same time. Maybe with some omega. It also has some radial size, plus r. Right. Now, they did not tell you the radial size of that bowling ball. Right? And that's where, see, like the first time I read that question, I would have thought, it feels like that would be important information. But the fact that they didn't give it to you, maybe that's a hint that it cancels out somewhere, right? That we don't know how big this bowling ball is. Right? Because K translational, that just means linear, is your classic 1/2 mv squared that goes back a few weeks in this class. Okay. But K rotational, well, that's 1/2 I omega squared. Okay? And, well, hold on to that idea. Let's just plug and check for this one, because we can just do this one real fast. Okay. So 1/2 mass of the bowling ball, 5 kilograms. Times v, 2.5 meters per second, being squared. So many joules of energy associated with them. So 1/2 that squared. I'm looking at this many joules of kinetic energy just associated with moving in a straight line. Right, so you point a radar gun at it, it says it's moving the speed, right? You know the mass of the bowling ball, that many joules of translational kinetic energy. Now for the rotational kinetic energy, see here's what I would want to do, like my go-to approach. I would pop up in a textbook, I would say, oh, the bowling ball is probably best approximated as a solid cylinder. Solid cylinder, I value is 2/5 mr squared. So I would do something like this. So this is 1/2 of, I'm going to substitute out that I with 2/5 mr squared. And then work my way from there. But dang, they didn't actually tell you what the radial size of that bowling ball is. But you know what? Omega. Do you guys remember what omega is in terms of v? V over r. V over r. Yeah. Okay. So to go back and forth between, and don't forget that's also squared. Okay. To go back and forth between v in meters per second and omega radians per second, remember, you either like multiply or divide by r, depending on which way you're going. Okay? If you ever forget, remember v is in meters per second. So if you divide by meters, they'll bring you down to just radians per second. Sometimes radians is kind of like an invisible unit. Okay? If you start with radians per second, multiply it in your r, you get back to v. Okay. Do you guys see that this r squared and that r squared are going to point, point, goodbye? You guys see that? Okay, so here's where we're okay. So the fact that they never told us the radial size, that's where it cancels out, because that's being squared cancels. So we're back to being okay. Yeah, what's this? Okay. So I got 1/2 times 2/5 times mv squared. So the m was so many kilograms. The v is so many meters per second. That is being squared. See how many joules of energy are associated with rotating, like rolling. Okay. So So 1/2 times 2/5 times mass times speed squared. Looking at this many joules of kinetic energy rolling. Okay. I'll go back to that first one. 1/2 times 5, because I rounded this number, but there's another point that I want to make. Okay. This is actually 15.625 joules. Okay, to get all the digits in there. Okay. There's a reason I do that though. Okay. Because the fact that they, again, never told you the radial size of the ball, okay, also hints that there's probably an exact proportion between translational kinetic and rotational kinetic, regardless of how fast the bowling ball moves. Oh, yeah. Okay.
Where did you get the 2/5 from again?
The 2/5. Yes. Great question. That comes from this table in the book on page 257. It says that the rotational inertia associated with a solid sphere. So I'm saying the bowling ball is probably best approximated as a solid sphere. Yeah. So it's like 2/5 m r squared. Okay. So I bet that regardless of how big the bowling ball is, how massive the bowling ball is, how fast the bowling ball is moving, I bet that these two numbers are probably some consistent ratio. Right? I wonder what that ratio is. Well, let's see if we can figure out. What is 6.25 divided by 15.65? Oh, it's 2/5 exactly. Look at that. That number divided by that number is 2/5. They said. So that's maybe a good tidbit to hold on to, just in the back of your mind. Okay. Oh, now that was part A and part B. Okay. Part C says what's the total kinetic energy. So C, K total. Wouldn't that just be K translational plus K rotational? Right. So it's going to be, say, 15.625 joules plus 6.25 joules. And I'm looking at 21.875 joules. Right. That's really too many digits. Maybe I could say like 21.9. That's about all I could really know. 21.9, right? 21.9 joules. Total mechanical energy. Right. Part D says how much work would you have to apply to it to bring it to a stop? Wouldn't it just be negative that? So if you if you push on it in the opposite direction of its motion, take that much energy to bring it to a stop. Okay. Is that right? All right, now the main problems. Number 2, find the net torque on the wheel in this figure about the axle through O. Point O is like the origin point in the middle. Perpendicular to the page. Take the small radial size to be 10 centimeters and the bigger radial size to be 25 centimeters. Okay, well, I might change the numbers again like I usually do, but no idea. Now, before I get solving this one, mention a detail about how they phrase this question, which would be a little bit different from how AP would phrase this question. Okay. Notice they said find the net torque about the actual perpendicular to the page. What does that mean, perpendicular to the page? Because couldn't this be like an XY plane, like x-axis, y-axis, XY plane? Okay. And then, do you guys remember back when I told you guys about torque? One of the details I mentioned was something called right hand rule. I showed you guys an animation, right hand rule. Okay. Let me take you guys through that. Right. So, see this 12 Newton force right here at this radial distance A. So here's R, radial distance R. Put your fingers in that direction, and then curl your fingers in the direction of the force F, and see how my thumb's going to point out of the page, right? Out of the page. That's like the Z-axis, isn't it? Now, this is sort of a math trick, but it works really well if you have like crazy vectors going on in 3 dimensions. You guys remember that cross product example I took you through with the matrices and that whole bit? Right. So that'd be like torque defined out of the page. Right? And then, so you take this 9 Newton force that's trying to make this whole thing go like sort of like clockwise. Okay. If I do an R cross F for that, see how my thumb points into the page for this force, right? And that'd be like a negative torque. So you have like a positive torque and a negative torque. guess that. Okay. Now, everything that I just said is one perspective on torque. You could totally see that if you take a physics in a college class, but AP does not use that thought process at all. AP just calls torque clockwise and counterclockwise, which is maybe a bit more intuitive. So it's a little bit different from your book, though. Okay. All right. Here we go. Let's figure this out. Number 2. All right, so we got, so your big wheel, small wheel, everything's rotating about the middle. Draw some that's I don't know what that whole confusing about. Yeah. I don't know what that whole 30-degree angle is about, because I'm gonna, yeah. I know I told you guys torque is RF sine beta. I think it's just gonna be perpendicular to this lever arm anyway. I'm just gonna assume that this and this are perpendicular. Right, so I'll use that approach. Okay. I'll change the numbers a little bit. It goes 13 newtons. Make this radial arm, say 11 centimeters. Make this radial arm 26 centimeters. Make say this force, which is again perpendicular to that. Let's make this 10 newtons. And maybe I'll have this pulling here at like 11 newtons. I'm trying to make everything proportional. I should make this one a bit longer. 13 newtons. Okay, so you got 3 forces, 2 different radial locations. Right, what's the net effect? Is this thing going to spin clockwise, counterclockwise? How's it going? Okay. And so torque is R cross F. I'm going to find 3 different torques and just add them all up. Of course, 2 are going clockwise, and one says, no, let's go back counterclockwise. So, yeah. Right, so I'll start with the counterclockwise one, because that one's usually treated as positive. So R cross F, right? We've got 11 centimeters with the force of 13 newtons. With so many newton centimeters. Okay. I've got the next one would be 26 centimeters and 10 newtons. Okay. And that's going to be negative because it's going clockwise. Okay. And the third one is also at 26 centimeters. Got 11 newton force, negative because clockwise. Add those 3 up. So what is 11 by 13 minus 26 by 10 minus 26 by 11? I'm looking at negative 403, and that would be Newton centimeters. Like that. We're gonna have you guys do a torque lab sometime probably next week, and I'll have you guys measure all your forces in newtons and also your distances in centimeters. So you'll have torque units that are kind of like that, Newton centimeters. Right? Usually torque is in like Newton meters, the most likely unit you'd see on an AP exam. All right, so far. All right, let's do number 11. Says find the X and Y coordinates of the center of gravity of this uniform sheet of plywood that's like this L shape. Right? Hint, the mass of any segment of plywood is proportional to the area of that segment. Okay, so it's just like uniform density, just a flat sheet, right? And then you can use this area as a proxy for like individual mass parts. Right, so center mass. One property of center mass is just the point that you can balance balance on your finger. So like if I try to say this paper's upside down, right? Could I balance it on this point right here? No, because there's going to be a torque and it's just going to fall over this way. Right? Could I balance it on like this corner over here? No, that doesn't make any sense. It's going to be a torque that's going to go this way. But there's a center mass probably somewhere about, I'm going to guess right about there-ish, right, where I could actually like balance it. Right? Sometimes there's a center mass that's actually off the object. Like if this was like a ring, like it'd be like inside the donut hole, right? Which would be like where no mass is at all, right? But something like that. I guess it's probably pretty close to that point though. So how can you figure out exactly where the center mass is? Well, before we solve this problem, I'm gonna show you guys how to solve a more basic problem because that's a two-dimensional center mass question. Right? And I do have a demo lined up for you guys too. But save that for another day. Okay? But what if you just wanted center mass in one dimension? Like center mass in one dimension. So center of mass. And maybe you have a meter stick that has some mass, and even though its mass is distributed over the whole thing, you could say, well, its center mass would be its geometric center, maybe at the 50 centimeter mark, something like that. So you got the mass of a meter stick. Right? And maybe I'll throw a couple of weights on this. So maybe at one end, I'll throw a little tiny lab weight, and on the other end, I'll throw a big old lab weight. Okay? Now, if you wanted to balance that on your figure, then what would make more sense? Should be right at the geometric. Here, I'll call this mass left and mass right, maybe something like that. Okay. Should I balance it right at the geometric center still? Should it be closer to the small mass? Should it be closer to the big mass? Yeah. Probably right about there. That's probably where about the center mass is, right? Center of mass. Probably like right there. And so how could you calculate that? Say if you knew what these masses were and what their locations were, something like that. Right. Well, here's the formula. So x bar, there, sketch these out. Now I should go all the way to the meter stick. Okay. I'm gonna call this x bar. So like, you guys know in general, if you see a bar over a variable, it means like average. I think you guys saw it with like average velocity, something like back in the day. Okay. It's equal to, it is. Okay. Say like mass 1, location 1, plus mass 2, location 2, plus mass 3, location 3, all divided by the sum of the masses. I know that doesn't exactly match my picture, but you guys get the idea, right? Okay, say mass 1, mass 2, mass 3. Say the meter stick could be mass 2, say something like that. Okay, so we've got mass times location for each individual bit, all added up. And then if you divide up by the sum of the masses, you see you're going to be left with like some kind of location value. Okay. Do you guys see too that, say if you pumped up one of these masses, say like it took this mass on the right, call it mass 3. If I pump it up like really huge, like a lot of mass, isn't the center mass going to move towards that location? It's kind of like its mass times its location, like it's giving more influence to its location for the center mass, right? Is that? So in general, x bar is equal to the sum of m sub I, x sub I, and then I could be like a counter, like 1, 2, 3, 4, 5, right? All divided by the sum of the mass values. Okay? So there's a general formula for center mass. Okay? Now that's of course in just one dimension, just along say an x-axis in this case. Okay? But your book question goes into 2 dimensions because we're looking at like a piece of plywood. Okay? But that's okay because all we have to do is apply exactly this to the x-axis and then do the same thing along the y-axis. We're going to get coordinates for exactly what the center mass is, like an x-coordinate, a y-coordinate. It'll be like x bar, y bar. Okay? Is that? All right, so number 11. No, they did actually give us coordinates, which was really nice. So helping us out a bit. All right, give us an x-axis, the y-axis. Here's the point 0, 0, the origin point right there. So this is 4 meters. This would be in meters, right? Meters. 4 meters, 8 meters. Then we got, this is 2 meters, 4 meters. Go ahead and use the book values here. Okay. So what we can do is we can split this up into individual parts, maybe like rectangles, right? That would make more sense. maybe this rectangle, this rectangle, this rectangle, and then solve it from there. So thing. Okay. Actually, maybe even a simpler mathematical approach would just be to break it into two rectangles. Okay. Maybe we have a left rectangle that's pretty big and a right rectangle that's kind of small. Okay. Maybe I'll do that. Because I can see right away that the center mass on the left rectangle is going to be this point right here. It's going to be at the point 2, 2. And the rectangle on the right is going to be at the point 6, 1. Is that right? I bet the center mass is probably somewhere along the line between the two. You guys think the center mass is probably somewhere on that dotted line I just made right here? Somewhere. Where do you think the center mass is closer to? The one on the left or the one on the right?
On the left.
Yeah, it's got to be the left because it's like twice as massive. It's probably right about there, isn't it? Okay. See how we could do this. Okay. So, well, that's probably what I just did, like right here. Okay. So mass times location for each one. So for the big rectangle, or x bar, going to be, remember your book gave you a hint. It said the mass is proportional to the area. So let's just play off these areas. You see I've got basically 2 units of area versus 1 unit of area. Okay. All right, so let's do 2 units of area times an x bar of 2 plus 1 unit of area times an x bar of 6. Okay. Then all divided by the sum of the mass, which is 2 plus 1. Just like that. All right. What is that? That's 4 plus 6 is 10. 10 divided by 3 is 3.33. Right. 3.33. Well, there's 3. 3.33. That's right about here. There's 3.33. Okay. Okay, so looking good so far. Looks pretty in line with what we've been thinking so far. Okay. All right, now what about the y coordinate? So similar thought process. Y bar is equal to, it's going to be a big old fraction. Okay. We're going to have, so 2 units of mass times the y bar of 2. So 2 by 2 plus, this is 1 unit of area, mass, okay, times a y bar of only 1 for that individual piece. Then divide by, well, the same 2 plus 1, just like for the x values, right? Okay. So that's, let's see, 4 plus 1 is 5. 5 divided by 3.
No, 1.6.
1.67. Right? So 1.67. That's right about here. 1.67. Take us. Oh, yeah. That's sort of where we were thinking to start, right? Doesn't that look like you could balance this whole L-shaped piece of plywood right on that point right there? Right? Looks pretty well balanced, doesn't it? That's the center of mass of this thing. Right there. It's at the coordinate 3.33 over 1.67 up. There you go. There's the center mass of that thing. There's good there. Tell you guys what, that's as far as I got in my last class, so that's gonna be our pause point today. Let's see if you guys have a VTD